So welcome everybody today. So we have next seminar. So basically, I would like to continue the previous topics, and I would like to talk about the quantum communication and quantum logic in CMOS position-based qubits. So basically, maybe a brief reminder. So as you can see, there is a definition of Hadamard transformation that is given by equation 1, right? It's a matrix, and then basically we need to find out the way of representation of this Hadamard transformation in physical systems, and yeah, that's a good point. All right, yeah, so there's 1 over square root of 2 in front of it. So basically, we have this this position-based qubit, and this position-based qubit is you can say a semiconductor nanowire on which we have placed a metallic gate, and then basically electron wave function is split into 2 regions. So effective electron can be at 0.1 or 0.2. And there are characteristics oscillations of occupancy. So if this wave Schrödinger wave function has at least 2 energy levels, there are characteristic frequency of occupancy, and this frequency of occupancy is proportional to energy difference between 2 energy levels that are occupied. So it's well known from quantum mechanics that only when 1 level is occupied, there is no oscillations of occupancy. So this is necessary condition. So basically, such system as here can be represented by this by such potential, and this is very convenient because we can always have we can place the chain of such red bars. So we can have a chain of coupled quantum dots that can be controlled electrostatically. So that's the magic of this approach. Obviously, there are many challenges in the meantime. And first thing is last week we have mentioned about Rabi oscillations. So this was nothing more as a pumping energy from energy level 1 to energy level 2, or from energy level 2 to energy 1. And this allows for controlling the state of such qubit. Okay, so how we might proceed? So basically, you already know that we have this. Yeah, I need to make it smaller. Yeah, so you already know that we have this position-based qubit expressed by these projectors. So that there is probability that there is localized energy AP1, so that the electron stays on the left side, and probably the localized energy on another node on the right side, and there is a possibility for continuous transfer of electron presence from left to right and from right to left. So there's this Hoping constant T. And this is a little bit tricky because, let's say, electron energy, kinetic energy is both encoded in localized energy and to a certain extent in Hoping energy. And this, so this is the Hoping energy. This is energy that is participating in electron, that moves with electron in a way. And this model can be viewed as minimalistic view on Hubbard model. So, but still, this model is in this form is one electron model. So there's no more than 1 electron. Maybe in some time I can move to the more complicated case when we have at least 2 electrons in such system. And now. So this is the case, the equation 2 is the case of electron that is non-interacting, and and then there is equation 3. So equation 3 is the case when electron is interacting with external electromagnetic field. So you can change the biasing of certain gates in your structure with time. So basically there is a time-dependent Hamiltonian, and it allows for transfer of electron state from the ground to from excited to ground, or from ground to excited. And you will see later that well, and now is the issue how to express this. So we need to have everything in uniform representation. So this projector. So there is a basic state in position representation that is referring to Wannier function. Wannier function is maximum localized wave function, and on the left side, this is denoted by this such notation, and on the right side by WR. And Wannier functions obviously are known in condensed matter physics, but here they are used in the context of nanostructures. So basically, if you have a Schrödinger equation, Wannier function is linear superposition of two energy levels at least, and then it just express maximum concentration of electron on one of the sides. That's how it's defined. So you can either have a picture of electron presence by wave function or by Wannier functions. Wannier functions are orthonormal, and so they're orthogonal and normalized. Yeah, and because of this technological scheme that is because of this effect that electron is designed to be in a position-based qubit, a Wannier function is the most convenient representation of the state of position-based qubit. All right, and then there is of course definition that Hamiltonian acting on excited state, it gives an energy 2 times excited state, and the same is with ground state. So Hamiltonian acting on ground state, it gives ground energy times ground state. And so this position-based qubit is represented Hamiltonian in such a form, as I already mentioned a few times, and basically, if you have a zero magnetic field, then these Hoping terms are real valued. However, if you bring external source of magnetic field, what happens is that this T coefficient becomes a complex value. So there's a phase imprint on the wave function, and this phase imprint makes those two coefficients conjugate. So they have like opposite phases. Yeah, and then you can deal further. So you have equation 5. So again, it's for Hamiltonian. You can find its Eigen Energies. They will be EP minus T and EP plus T. So there are two energy levels that corresponds to tight binding model. And obviously, you can look for its ground state. There is by formula 7. So there's like antisymmetric wave function in Wannier representation, and excited state is symmetric wave function. So obviously in general case, any wave function can be decomposed into symmetric and antisymmetric. So that's how it is. Yeah, and then so you will see from our considerations that we have the state of qubit by equation 9. So it's an energy representation, then eigen vectors, kind of trivial as to you. And then we have equation 11. So Hamiltonian acting on our yeah. So that's how we can relate. So this is Hamiltonian acting on a grounded excited state is expressed in such a way, and then we are using this. We are changing the basis. We are changing the basis with use of our previous results that was given here. So you will see that this is exactly the Hadamard matrix that is encoded in such representation. So basically, you can write that such state is so such vector is represented by Hadamard matrix and by Wannier functions. So and since so you can apply twice this matrix to both sides. So you can move from here to here. So you always have this Hadamard matrix, and this obviously. So you can rewrite this results in the following way, that changing from such vector of energy representation to position representation requires Hadamard's transformation. And now we need to utilize it in certain logical operations. So in the most general case, so the quantum system can do it in such a way. And then there is this linear combination of excited and ground state. And again, we can express this in form of Hadamard matrix. So you see that you see how this is expressed. Now the next issue. So how to say? So if you want to make a logical operations, let's say, what you are going to do? So basically you can change the occupancy of. You can span the vector your logical state by Wannier functions, and then in energy representation it will have the state after Hadamard transformation, for example, or you can do reversely. All right, so now how to deal with this kind of Rabi oscillation terms. So we already specified this those equations at the very beginning. So this is the term that is here responsible for heating. So there's a transfer from ground to excited state, and then you can move from energy representation to Wannier function representation. That's how it's done here. And obviously you obtain such term 16. And doing things in a quite analogical way, you can have a kind of cooling term when your state is going from excited to ground. And then again, you need to make this algebra of this changes in your presentation, and basically you end up in such terms as, again, by equation 17. All right. So if you plug it to the Hamiltonian, then the tight binding Hamiltonian, what you will have is you will have this this modification by F1 and F2 functions. Just to remind you, this F1 was responsible for heating up and F2 for cooling down. So those functions are here, and so what you need to know. So these diagonal terms must be real valued, and so F So and also, and this antidiagonal term needs to be Hermitian conjugate, and this will bring you certain implications. And yeah, so essentially, yeah, just not to mess up. So yeah, so we if we want to maintain this Hermitian state of this Hamiltonian, we have to put some extra requirements for those f1 and f2 functions. Right, I'm just looking if everything what I placed was okay. Right, so that's a philosophy of approach towards Rabi oscillations, and basically, yeah, that was already discussed 1 week ago. All right, so verse just deals with equations of motion that can be easily derived. All right, so I move back to my previous talk. So basically, the previous talk title was towards quantum internet and numerical communication in position-based qubits. So how things are done. So again, we start with this chain of two coupled quantum dots. Then we have this Hamiltonian emotional way expressed by Formula 1. And then we have two Eigen Energies. This is the most minimalistic model of position-based qubit. And then we have the eigenstates that could be represented in a spinor or in a such cat form. And then we have these changes of the basis of the system. So basically we have Eigen Energies E1 and 2, eigenstates E1 and 2, and then there is this this matrix S that is acting. So this is this Hadamard matrix. So it acts on such type of state. All right, so we can deal with very specific cases for the given system. So, for example, we can consider the situation where when we have a infinite barrier between a left and right quantum dot. So electron wave function is split into two, and there is no transfer. So the Hoping constant Ts is set to 0. So in such case, we are dealing with equation number 4, and then yeah. So the evolution is quite simple for this equation with time. All right. So then obviously we can also formulate this Unitarian matrix that describes the evolution of the quantum system. Yeah, so this is already kind of a little bit nasty expression, number 6. So we have this essentially 3 main parameters, AP1, AP2, and there is a possibility of phase imprint. And there is a Ts that corresponds to Hoping constant. So then there is possible decomposition of this spinor into two eigenstates as given here. All right, so this was already kind of discussed, and last week we talked about this placement or just of this position-based qubit in electromagnetic cavity. So it could be placed in nearby to electromagnetic cavity, and then there are just the Hamiltonian of cavity can be is essentially expressed by electric field square plus magnetic field square. And so there's equal distance between Eigen energies, and this is a bit similar to harmonic oscillator, where E field plays the role of position and B field plays the role of momentum. So obviously there is not possible to determine both momentum and position at the same time in a quantum mechanics. Then we are dealing with this so we know already what is the Hamiltonian of position-based qubit in most minimalistic way. We know what is with this Hamiltonian of cavity, and then we need to know what is this Hamiltonian of interaction between qubit and cavity. And then this is basically the effect of dielectric dipole that is interacting with external electric field. That's how this dynamics is of interaction between electromagnetic cavity, electromagnetic quantum cavity. That's supposed to be underlined. All right, so there's equation 8. So basically, we have such, so we have analogy to, so we have this is like position, and so we have the, so finally it turns out that if qubit is in excited state, the result of this interaction is that it goes to ground state and it emits photons that is absorbed by a cavity, or it can be it can be the ground state, and after a certain time it absorbs photon and becomes excited. So there is such exchange of photons that is between a qubit and cavity. That is the signature of this interaction. So this is mediated by photons. Yeah, and in such case, in most minimalistic way, the qubit, the quantum state of a system can be decomposed to a four terms. And so this is ground state of this cavity and ground state of this qubit. Ground state of cavity and excited state of qubit. Position-based qubit, again, we can have an excited state of a cavity and ground state of a qubit, and both excited state of cavity and excited state of qubit. So that's how it is. So it can be represented by a vector of length 4, and obviously there is normalization condition that needs to be fulfilled. So far I described the case of electromagnetic interaction of position-based qubits with electromagnetic cables. So basically there are some kind of challenges in this picture, since this picture is very much oversimplified. First of all, if we have such scheme as given here, if there's an electromagnetic cavity with a hole, there will be a leakage of photons from a cavity out of space. So this will be effectively seen as dissipation, and the dissipative term. So simply cavity is losing its energy, and and photons that does represent this energy of cavity. On the other hand, if you place your position-based qubit very much inside the cavity, what happens is that you deformed the electromagnetic state of cavity, but at the same time, as we are changing its frequency of oscillations, but at the same time, you are, how to say, increasing the strength of interaction between electromagnetic cavity and qubit. So that's a kind of good feature. All right, so basically this system is most minimalistic way described by matrix 4x4. And this is not sufficient to have a communication because you need to have at least two position-based qubit. However, in such configuration, you will have entanglement of matter and radiation in such a form. And basically, if you have a resonant cavity with two holes, that doesn't have to be on the same side, could be even better on the opposite side. It happens is that you might generate such configuration that so in which this position-based qubit is interacting with resonant cavity, and at the time this position-based qubit is not interacting with another position-based qubit. So that's so those qubits are kind of isolated. Yeah. So and then you can create a system in which you entangle this position-based qubit with resonant cavity, and also this cavity is entangled with another position-based qubit. So there will be indirect entanglement. So there will be indirect entanglement between first qubit and another qubit. So this is actually a picture from last week. However, you need to be realistic. So in very practical applications, you need a long line that will deliver your one electron and take it out if it's necessary. And if you want to prepare the state of position-based qubit, you need external dipole antenna, and that will generate this radio frequency signal.
Right.
Hello. Yeah. So basically, you need this dipole. Maybe you should write a message to him that he's not muted.
You can mute as a host.
All right. I never do such things, but yeah, I need to find this option. All right. Anyway, all right. So let me move on. So basically, you need. This is the minimalistic way of controlling the state of each qubit, and yeah, and yeah. So so that's how it is. So you pump electron, you localize it, it interacts with resonant cavity with an upper electron. All right. So and now, what is the system Hamiltonian in greater detail? So we specify the basis. So how it can be done? So basically, what we have is qubit and cavity. Hamiltonian is just consists of diagonal terms. Other terms are zero. And this qubit cavity terms has anti-diagonal components, and this is metric representation is given like here. So this matrix is Hermitian, and this matrix is Hermitian. So yeah, so basically you can write it in that way. And what turns out that this entanglement that might take place in the given system is only generated by this qubit cavity term. So you need to be able to increase this strength of interaction of resonant cavity with a qubit. So you can intensify the electric field, or you can try to place qubit as much to the center of cavity as it is possible. However, it brings another type of complications, right? So that's a total Hamiltonian is number 11. So you see this Hamiltonian, and then now you need to specify, you need to find its Eigen Energies. Yeah. So what happens is that you have 4 Eigen Energies. So E1 and E2 are not so interesting, but other are more interesting. So they are given like that, and then they already entangled states. All right. So the given system here has 4 Eigen Energies, and these Eigen Energies are given by equation 13. And also those 2 terms are specified. So here you have this G1 G1 term that generates with this interaction between electromagnetic cavity and qubit. All right. And now what you need to do is to evolve, to search for evolution of system with time. That's a bit lengthy. But it can be done in an analytic way. So there are formulas 15, 16. Yeah, and yeah, then you can see how things are described. All right, so I will move on so I can move later to this logical operations, at least philosophy behind logical operations. So it's kind of tedious, but if you have 2 qubits interacting with a cavity, then you end up in matrix 8 by 8. So this is formally expressed in such a way as equation 22. And yeah, and then basically again you have, maybe I will magnify this matrix. So you have diagonal terms that corresponds to non-interacting free quantum systems, and then you have this off-diagonal terms, in particular this anti-diagonal terms that describes this interaction. Yeah, so they are given like here. So you can make some radical assumptions in this model. If you symmetrize those qubits, also if you set such condition as specified here, you can get this analytical states later. So there is a kind of algebra ongoing that describes those states, right? So various of those states are entangled, and so you can exploit this property of entanglement much later. All right, so that's a kind of algebraic exercise how to deal with that. All right, so maybe I will skip the other part. It's when you go into detailed computations, what is necessary is just to be able to compute the dipole of what is the electric dipole of a qubit. Is a difference in occupancy on left and right quantum dot. you need to have a 1 minus 1 on this matrix acting on a given quantum state in linear function representation. And doing so, you can get this dipole moment, of a qubit. So if you have the situations at the very beginning, you will see that in ground state or in excited state, this dipole moment is 0, but it's if it's in between, that is non-zero. All right. So now, obviously, you can conduct certain considerations on electromagnetic cavity and on electric field, and get various this electron, this photon wave function, and that is kind of described here for confined photon in a cavity, and then you will see that there are some space variations of this wave function. All right, so yeah, so let me move on. So yeah, so maybe I will go to more kind of exciting. So it's kind of tedious to compute this interaction between this electric field dipole term and I'm just trying to. So if you have a Hamiltonian, it is expressed like here. And all right, so yeah, so in this notation over here, A, B, C, and D are expressed in such a lengthy formulas. Since you can express ground state by a linear combination of qubit position on the left and right, and the same is with excited state, the position of electron on the left and right side. Yeah, so so you end up in such type of matrix. Yeah, there is a lot of algebra involved here. You will get such dipole moments in way as given here. Again, you can do same algebra for quantum electromagnetic cavity qubit interaction, and you will get these expressions given by equation 46. All right. So finally, so before you have seen this Hamiltonian in energy representation. So there was four elements of this base. So there was a tensor product of cavity ground state times qubit ground state plus blah blah blah. And now we have moved to such a representation that is more intuitive from the point of view of nanotechnology. So this representation is that that it's convenient to use linear function representation for characterization of the state of positionless qubit, and then changing this base into such base as given here, as you can see. Then this interaction matrix has two of square blocks, and there is explicitly written the position of electron. So those terms 8, just to remind you, terms A, B, C, D were connected with this Eigen energy. So they are, so this is, ground state is as states made from two minor functions on the left and right side. And also excited state is the same. Yeah, so so you have those terms. Yeah, I'm just looking for yeah, and then there was a description of you in such a way as given here. So that's you and you Daga. Yeah, so finally you can arrive to such expression as given by 147. All right. Yeah, so that's obviously you can continue such considerations for two qubits interacting with quantum electromagnetic cavity. All right, so this is for the case of non-interacting qubits with electromagnetic cavity. So this is us here. All right, so sorry for this type of lengthy expressions. Maybe I move to more kind of all right, so yeah, maybe are there any specific questions at this stage? All right, so maybe I move now back to this description of quantum gates. So basically, maybe at first briefly about this philosophy of this quantum gates. So this is very simple philosophy. Actually, it's a philosophy of charge balls. So if you have wooden charge balls and certain corridors, the question is how to design the corridors so certain functions can be utilized. And yeah, so I will omit this part of, yeah, so yeah, maybe at this stage I also mentioned something about these Rabi oscillations. So usually yeah, if you have no shining of no presence of radio frequency field, you will see that probability of occupancy of given energy level is flat. However, if you shine light, there is exchange of occupancy of energy 1 and energy 2 as in way as given here, right? So you can translate this changes of occupancy of energy level 1 and 2 into the changes of occupancy on the left and right side, and this will be as being here. So it is a bit more complicated this behavior. Yeah, during this process of Rabi oscillations, there is a change of phase between left and right quantum dot. So essentially the phase of left and right is plotted here, and this difference is plotted as here. So this is under the circumstances of very strong electromagnetic signal shining the qubit. All right, and maybe I move to more kind of yeah. So basically, so let me start with this treatment of those quantum gates. So we have two electrons at two parallel lines, and they are each electron. So this electron can be place 1 and 2. So at upper line, and then we'll replace 1 prime, 2 prime, and lower line, and those two lines can interact. So you have three gates that control the state of qubit between 1 and 2, and again 3 gates voltage control that can control the state of qubit between 1 prime and 2 prime. Yeah, so this is swap gate. This is the way how you can do swap gate. Then you can analyze these properties of two double quantum dots on the line, and then it's not surprising then presence electron at 2 in first line will imply presence of electron at 2 prime in the second line, and so on and so on. So this minimum electrostatic energy can be maintained in the whole space, or in other words, there will be Coulomb propulsion. So so in a sense you can say that this is synchronized with this state starts to synchronize with that state. That's one of the possibilities. All right, so yeah, so let me just mention maybe one more thing. If you have a Josephson junctions across one line, what happens is that they also try to have a synchronized phases. Yeah, it's good to also to think in that way. All right. Maybe I will. So this swap gate also can be implemented in a such way that not necessarily two parallel lines, but also at perpendicular lines. So that's one of the ways of doing it. However, there will be huge possibilities when we are able to control the ground states of the lowest potential levels of quantum of 1 and 2, or 1 prime and 2 prime, and this can be achieved with electrostatic control of these gates polarizing the position-based qubits. All right, so let's move on. Yeah, I still have to. Yeah, so maybe I will take some questions if there are some questions today on that subject. Maybe one more kind of trip just to see how things are done. So maybe I will change this. Yeah, please give me a second. So I try to download some. Yeah, so I hope it's visible. Yeah, so I just read the last. So basically, this was this philosophy of this repulsive balls, which we already discussed, and this entanglement was due to the fact that the wave function is diffusing here, and if there's non-zero Hoping constant from this point to that point, also here there will be entanglement between those two parallel lines. Yeah. Okay, maybe a few things more. So how to read the state of position-based qubit is also kind of tricky. So there is no one way of doing it. So you can read either the amplitude of the, so you have the localized wave function to places here and here. So it's effectively represented by coefficient of frequency A and B. And when you raise the gates, this wave function is if you raise all the gates, this wave function is tending to spread. And doing so, you will see two peaks, and these two peaks in your current flow will correspond to the presence of wave function to this B and to this A. However, if you want to get the phase difference, you have to raise the metallic gate 3 and then NB and B, and that might have a different phases. We might will go for interference. So by interference, you can obtain this phase difference. All right. So here was the scheme of phase rotating gate that was printing the position-based qubit. Yeah. So one way of phase of control of phase difference was by external source of electric current or external source of magnetic potential. Another way is by changing the bottoms of a position-based qubit. So so if you have bottoms at the same level, the wave function on the left and right side will evolve with same rate, the phase of wave function, and if the bottoms are different, this obviously has the impact on evolution of wave function, and then simply this can be used in setting the phase difference across position-based qubit. All right, so I guess that's kind of main part 4. Yeah, and there is a possibility of converting the state of position-based qubit Eigen energy representation to this sorry, so this was Wanner-based qubit, and this was Eigen energy-based qubit by set of gate operations. All right, so obviously you can think about more complicated structures, and here is the scheme of CNOT gate. So you have a CNOT input, so you should the electron you place here, and this electron oscillates but cannot escape this area. You can have a CNOT control gate, so you inject electron, it stays here, it oscillates back and forth. And also you can have this output gate. On this output gate, you need to be able to read. So that's why it has such configuration that output qubit is generated here, and then you can do some specific readouts on it. Right. Yeah, and there are some analogies of this position-based qubit with a Cooper pair box, where you have controlled the state of one Cooper pair. It was given at the very beginning. However, there is a different nature of this control. Well, in both cases, you are using the biasing electric field. And both systems that's what's supposed to be mentioned are quite much subjected to coherence due to charge loss. Yeah, so you can construct this. You can also, so you might have this single electron Josephson junction or Cooper pair box, and you can have this qubit, position-based qubit. So you can have a position-based qubit ring, and this interacts with external circuits that are made from superconductors. So that's one type of interface, and another type of interface was already described by me. So you can have electrostatic qubits, and the charge here is such small that it's able to see the presence of qubits somewhere around here, and also here. All right, so I guess this will be enough for today. If you have any questions, please let me know. I'm not sure if I was too quick or something like that. All right, so we are going to continue certain topics. On coming week, I expect one guest, and I'm looking for his confirmation. All right, so if there are no questions, I suggest that we end up here. Okay, thank you. Bye-bye.
Bye.